So in this video, we're going to look at a case where we have to do repeated applications of the chain rule in order to get a derivative. So it says find dy dt, or find the derivative y prime for y equals the square root of t cubed minus 2 plus 2t raised to the 2/3 power. And what I want to recognize is that I have two function compositions going on here. I have this stuff on the inside being raised to the 2/3. So there's an x to the 2/3 kind of thing going on. And then I have a square root function sitting over here. And there's a t cubed minus 2 sitting inside of a square root function. So I've got two function compositions going on in this particular example. And so we're going to need to use the chain rule 2 times. If we get 3 function compositions, we would need to use the chain rule 3 times, and so on and so forth. So for this particular case, if I want to take the derivative, so I have y equals, and then I've got the t cubed minus 2. I'm going to raise it to the half. I probably want to write the radical form with the rational exponent instead to make taking the derivative easier to think about. And it's all being raised to the 2/3. So when I do y prime, this is the inside function, and the 2/3 power, the x to the 2/3 power, or t to the 2/3 power, is the outer function. So I'm going to apply the general power rule to the stuff to the 2/3. So it's going to be 2/3, the exponent comes down into the coefficient position, so it's going to be 2/3 times the stuff on the inside of the function, and then I need to decrease the exponent by 1, so 2/3 minus 1 is negative 1/3. And then I'm still going to have the stuff on the inside, so you do the derivative applied to the stuff, or taken at the stuff. But then you have to take the derivative of the inside function, the stuff on the inside. So we need to take d dt of all of that inside function stuff. So we get t cubed minus 2 to the half plus a 2t. And we need to multiply by the derivative of that stuff that was being raised to the 2/3 power. So I'm going to step down and continue to take the derivative. So it's 2/3 times, we've got the t cubed minus 2 to the 1/2, just rewriting that material. So negative 1/3 power. I could make this a positive exponent by moving it into the denominator. I don't think I need to. So times, now I need to take the derivative of this stuff. And I want to see that I have a t cubed minus 2 inside of the square root function. So first I'm going to take the derivative of the square root function. Again, I can use the general power rule on this. The 1/2 will come down into the coefficient position, and then decrease the exponent by 1. So 1/2 minus 1 is negative 1/2. And then you have the stuff on the inside, the t cubed minus 2. And I'm going to have to apply the chain rule to this, because this is a function inside a function. So it's going to be times the derivative d dt of the stuff inside of the square root function, the t cubed minus 2. And now I'm taking the derivative of a sum, which is just the sum of the derivatives. So I take the derivative of 2 times t. So this is a constant multiple of t. So it's going to be 2 times the derivative of t. The derivative of t is 1. So 2 times 1 is just 2. And then close off the parentheses. So equals. I still have another derivative to take right here. So it's going to be 2/3 times, I've got the t cubed minus 2 to the half plus the 2t all to the negative 1/3 power times, I've got the 1/2, the t cubed minus 2 all to the negative 1/2 power times, now I need to multiply by the derivative of t cubed minus 2, so apply the general power rule to the t cubed. You get 3 coming down into the coefficient position times t to the decrease the exponent by 1. And the derivative of a constant 0. So I really get this plus 0 when I take the derivative of t cubed minus 2. So I can just write times the 3t squared, and then plus the 2 that's already sitting inside there. And there we have the derivative where we had to do multiple applications, 2 in this case, of the chain rule. We could try cleaning this up and simplifying it, I think in this case, is probably not worth it.